going on to sell. Which I really got to, that's why I want people in mind that. Hopefully the red light. Oh, actually, I have them. I get started in there. I saw it. Okay, Trevor, how are we doing? It's, in doctor's grade, and I'm gonna be. Working? You have that test yet? Doctor's grade. And then Jersey was the third time Jersey school. So one Jersey. Then always being close to the other. It's hard to the spirit was from the illusion from the. But how to do that. Yeah, I'm not big on and we're going to get started. Wow, I cannot. I think this is the first time everyone stopped talking when I said that. The first time, it's a miracle. What? Okay, thank you for your cooperation. All righty. So our opening slide tonight. Where is he? There's Stan up there. Stan. So Stan contributed this very nice picture of the Cygnus loop for us tonight for our opening slide. Thank you for that, Stan. That's really a great picture. So, don't you guys like that? Turned out pretty good, huh? I like it. Very nice. And he put all the details down here on how to do it, or you can go ask him about how he took that picture. So before we get started, we'd like to find out if there's anyone here who this is your first time coming. You can raise your hand, tell us your name, how you found out about us, and what your interest is in astronomy, right here. Great. What's your interest in astronomy? Okay. Very nice. How about your friend next to you? Hi, daughter. So you just came because he made you come? Yeah. Okay. Got it. Oh, right here. Okay. Very good. Raven, right? And what was your name again? Abraham, right? Oh, there's still time. All right. Anybody else first time here? Oh, yes. Excellent. So which high school do you teach at? Okay, great. Well, you came to a good one. Justin's our guy tonight. He's the main guy. I was going to say something about that, but I didn't want to embarrass him. He got all dressed up just for us. Okay, anybody else? First time here? All right, very good. Here is our agenda for this evening. And okay, so we have an email distribution. And if you'd like to get on our email distribution, your best bet is sending an email to the second one down at the bottom, Star Hopper, and you get on email distribution. If you can't get that copy down or take a picture of it, there's some tear off tabs up there by the door. You can tear off one of those and send an email to Starhopper 457 and tell them you want to get on our distribution, and you can get our emails and know what's going on. Okay, reminder to presenters. So that's just me and Justin and Al, where Al went, and David. So just remember, you get up here, the mics are here so you can't run around. And this pointer is built in. Oh, the pointer's not on, Trevor. Yeah, I know. Let's see, what do I do? Hold on. Is it just right click on this thing? You got to get some help from Trevor here to get the pointer to work. Oh. Okay, so now the little red dot pointer, use that please so the people online can see what you're pointing at. All right, so our main speaker for this evening is Justin McCullum. I think everybody knows Justin, but I'm going to tell you some things about him that you may not know. He's right over there. Justin McCollum graduated from Portland State University and UT Austin with a BS and MS in physics, 2002 and 2005, and a PGP certification in AIML with the McCombs School of Business in August of 2023. Graduating at the top of the 2023 cohort. He is employed at Lamar University as the physics laboratory coordinator and departmental astronomy and space sciences instructor. He also works as a part-time education instructor for the education department at Space Center Houston. A longtime member of the following academic societies promoting astronomy and planetary sciences, STEM outreach with the Planetary Society and and American Association for the Advancement of Sciences, plus outreach and education on weather and climate sciences with the Union of Concerned Citizens, all since 2014. He received honors and awards with the various advanced observation programs of the Texas Star Party and the Texas Governor's School through the School of Education and Special Populations with Lamar University from 2007 to 2021. Justin recently joined the Department of Physics and Applied Sciences to conduct research, teaching, and developing courses for UHCL since January 2025 for a future pursuit of a PhD in astrophysics or space sciences with Dr. Samina Masood. So join me in welcoming Justin.
Some of that has been obsolete already, so.
That's 2 days ago. Oh, moving so fast.
Yes, I'm moving so fast. When I made this presentation, forgot how many slides there were, so we'll go through this as quickly as possible. One of the things is knowing about intrinsic versus extrinsic magnetic fields. So one is going to be inherent to the body, generated internally. The other one is due to outside influence. So you look on the left, that's going to be a dynamo generated by a planet in which it has fluids moving around that are heated up, creates the magnetic field. On the other side, on the right side, that's where you have those magnetic sheaths, like where is the, well, right here and right here. And this is the lines of the magnetic field of an outside body influencing something like a moon. So if we look at this, we should all be familiar, hopefully, with the basics of magnetism with the Earth itself. We call it the Earth's North Pole, but that's really the magnetic South Pole. Your needle points north because your north needle is attracted to the magnetic south. And then we have the magnetic north at the Earth's South Pole. Now, internally, the Earth has a dynamo. It generates equal amounts of positive and negative charges. It creates an internal electric field, energy gets shifted around, and then you have an induced magnetic field that flows outwards from one pole to the next pole, going from the, well, actually it flows outwards from the South Pole towards the North Pole, and that creates what we call a magnetosphere. It's like an umbrella of magnetism that surrounds a planet. Now, here you have sort of what we have, sort of the interlayers of positive and negative charges going from the inner to the outer core, to the inner to the outer mantle towards the crust. On the right side, because the Earth is spinning on its axes, you get columns of fluid in the outer core that circle around and have these interesting rotational effects, pretty much parallel with the rotational axes of the Earth. And that creates this swirling of magnetic fields that creates these curling, well, the swirling of the electric fields that creates the curling of those magnetic field lines that become organized as they travel out of the outer core in towards the inner mantle. And you get the magnetic field being generated. One of the things about this is the Coriolis effect, because we get that with the deflections of storms, hurricanes on the surface, where you end up having the storm somewhat physically detached from the ground. They experience the rotational motion of the Earth. You get the Coriolis effects. We see how the storms are swinging or being deflected. That sort of swinging and deflecting effect is what forms these columns of these rotating or spinning columns of charged metal ions inside the inner mantle towards the inner mantle and the outer core, but mostly in the outer core, and how it interacts with the inner core and induces the magnetic field of a planet. Now, I teach this to my students in the orbital mechanics course, is that it's a fictitious force because we are dealing with acceleration. And when you're dealing with Newton's laws with inertial frames of references, once they undergo acceleration, it's considered to be a non-inertial frame of reference. So, but we have to explain that as being a sort of a force that is a sort of a mathematical byproduct of the fluid sort of spinning about, so that we can apply some of the principles of Newtonian mechanics when dealing with the motion of this fluid before we get into the principle of how those ions are interacting to create that magnetic field. And so you have a video here, and you can see on the one hand, it would travel straight across in an inertial frame of reference, traveling at a constant speed, but because of two targets in which they're circling around a point, you see how it ends up as sort of a curved path. And the only way to explain that mathematically is to treat that as a Coriolis effect. Now, we get into the nature of magnetism. We have to realize that the Earth is internally heating within. So you have radiogenic heating. It creates a liquid fluid. That liquid fluid is going to be moving around material because of the spinning of the planet. It has angular momentum, and those electrons, you're getting charged ions moving about, positive and negative charge ions. That generates an electric field. We tell the students that the magnetic field is being induced because energy is being shifted from electrical to magnetism, and that's going to form the inner region of the magnetic field. You get material coming from the sun. It strikes the bow shock. It makes its way along the magnetotail. It travels back. It enters into these polar cusps right here at the top and at the bottom. And if the material gets trapped, depending on the composition between the very dense and not so dense plasmas, that forms the Van Allen belt. So we get these plasma belts around any planet with a magnetic field. They exist weakly with Mercury, but they also exist with Jupiter and Saturn. So here we look towards the nature of the magnetic field of a gas giant. It has all the various principles in terms of generating the internal magnetic field, but we have to remember, unlike the Earth, which is a rocky body, in the case of a gas giant like Jupiter, we have to look at how the dynamo is actually being generated by having a conductive material that's being moved around. That's the metallic hydrogen deep inside the interior of the planet, not at the core, but around the core. So you get sort of like a torus of the metallic hydrogen being moved around like a charged material, and that builds up Jupiter and forms Jupiter's electric fields internally, and that gives the planet its magnetic field. It comes in contact with the solar wind. It's being deflected about. The magnetopause is where the particles are slowing down because the field, the planet's field is starting to become having much greater influence in its local environment, and that will build up the amount of material and build up the charging of the magnetic field around it and the buildup of plasma around the planet. Naturally, it becomes more concentrated with denser material. Now, here is with Saturn. You can see how here it's Titan. So Titan's influence is somewhat mishmashy because you see here, you get the plasma belts. Now, you look at the temperature from the sort of the high, sort of like that sort of orangey color down to the blue. You're going from low to high temperature. Now, we have to remember when we're dealing with electrons, the electron volts for energy is comparable to temperature. So if you're going from 1 to 1,000 electron volts, you're going from cold material to hot, hot, hot material, very hot. And we can see how the plasma in the inner part, particularly as you go towards insolids, is going to be a lot cooler. It's going to be denser, but also it's going to be less denser as it gets heated up. And we get these sort of lobes over here coming from Titan, these sort of plasmoids, lumps of plasma being blown off. And the plasma itself is really being shot out of Saturn. It's not really condensing all that much, except for the much heavier material, which is mostly going to be water-based, and it builds up the outer torus with these plasmoids as they feel the spinning effect of Saturn gravitationally get shot out into space in the direction away from the sun itself. You have to remember that most natural satellites do not have their own neutral magnetic field. It's produced extrinsically. That means you got the magnetic field of a planet. It penetrates the interior of a moon. And if it's close up to the moon, you get flexing due to gravity, which can squeeze the moon in. It heats it up. Sometimes it's a sphenospheric, which is along the area just below the crust. Sometimes it can happen in the core. Sometimes it shifts between the core and the inner layer itself. So you get a buildup of ions, protons, and electrons of the plasma sheets as you get sheets of plasma as a result of eruptions. There's always going to be some eruptions, some ejections of material from these moons as they feel that tidal flexing, and that helps build up the amount of magnetism taking place around a planet itself. Because wherever there's plasma and it's charged, that's going to be influenced by the magnetic field of the planet and contribute to the planet's magnetism. Okay, now here we always deal with energetic neutral atoms. That is, they have enough energy to where they're not charged up, but they can still move at different speeds. And you can get something like a slow neutral atom. You get a fast ion with a lot of energy. It passes by a neutral atom, and it becomes somewhat ionized, so it picks up speed. Why do we talk about these? Because we find them a lot, particularly when they're being influenced by changes in solar gravitation, meaning that as the planet gets closer towards the sun, there's a greater attraction gravitationally, but also when there's huge eruptions of material, well, these particles can pass through a planet's magnetic field. They're not bound to any magnetic field. They travel at great distances. They interact with the planet's magnetic field, and they can alter the energy, mass, and momentum of these ENA particles, and that helps affect the dynamics of the interplanetary medium, the environment of our solar system between the planets. So there's always a trailing off the planet's magnetic field when it has an effect in the environment in our solar system. So this is the structure of Saturn's magnetic field. We have to remember that there are going to be these toruses, these sort of donut-shaped rings in which radiation is the result of buildup of material being blown out by the moons themselves. If the material is charged up, it's going to create these ring currents where we have material that is circling around the planet. It's going to be charged up, and it has basically electricity flowing from ion to ion in that environment. The ENAs, they come to the planet, they can get deflected off into space depending on how they strike at different angles to these shells of material here, these belts going from the planet outwards. There are these, what we call these wakes, where material is blown out, and if it's light or heavy, it's going to be trailing behind or going to be behind the moon itself, and that affects the density of material in these belts. All right, so most moons do not have a natural internal magnetic field. Saturn is a good example where we have these energetic neutral atoms. They tend to interact with the material around the plasma belts, particularly they're formed around Enceladus. And so you get these ring currents. These ring currents can affect the environment around the planet. You see down here, this is Enceladus's torus. So over here, we can see different types of radiation at different frequencies, and we can see mostly around here, this is going to be just water-based molecules being erupted from Enceladus. So that's the plasma belt around it. And when it gets interacting with those energetic neutral atoms coming from the sun, that can help actually enhance and swell the magnetic field. Like it's blowing outwards like a bubble. So you think of a planet's magnetic field, and that donut of charged material is making it swell outwards like a big bubble that gets bigger and bigger and bigger. Yes. That spacecraft that took that's I think that came from the Juno spacecraft itself. Yeah, that is aurora-like material. Well, it's actually a bunch of charged material along the surface along the atmosphere of Jupiter, and that's aurora material being spewed outwards. But that's due to interactions with those energetic neutral atoms. No, I'm sorry. That is Saturn. So yeah, it would have come from the Cassini spacecraft. Now we have there's known as the Saturnian kilometric radiation because of the long wavelengths of highly energetic radio waves, and you have to remember that relates to the aurora activity. In fact, when we see these when we see these powerful lighted lumps passing by, that usually correlates with maximum density of those big lumps in the Enceladus torus. As Enceladus passes by, we get these big lumps of material. They actually flow around. They actually strike the environment in the atmosphere above Saturn. You get the aurora activity. It interacts with those energetic neutral atoms, and you get those SKR signals. And it doesn't. But the odd thing is that we always think of the fact that Saturn's rotational axis, its rotational period, rather than its revolving period, its spinning around its axis, is related to its magnetic field. Because with these gas giants, you have to rely on the planet's dynamo when it's spinning on its axis. But now we're uncertain about that because we find that the Enceladus torus is actually, when we look at that, we're actually looking at the rotation, the revolution period in which the torus is circling around Saturn itself. So when we think about the 10 hours plus for when Saturn is spinning on its axis, that's actually due to the influence of the torus itself. So it's a bit of a uncertainty about the nature of Saturn's rotational period. Now we have here are the torus belts we got for Ganymede, which is mostly going to be carbon material. Europa is going to have a lot of water base. With Io, there's sulfur and salts. It's still uncertain as to the source of chlorine coming from Io, because we do get sodium chloride in the belts themselves, and they do increase in intensity. We get these ENAs because as we get radiation coming from the sun, those energetic neutral atoms will be shot outwards and be deflected out of the belts in different directions away from the sun. And we also, and remember that a lot of these ENAs can also be emanated from the natural satellites. We see those with the satellites of Jupiter, more so with Io itself. And it's not the fact that just, unlike Saturn, Jupiter is so intense in its energy that it can also generate its own ENAs. And if it had a lot more hydrogen, it would have indicative of a signature of the type of material and radiation coming from a star. But we also remember that torus belts themselves and that intense magnetic field around Jupiter, particularly with Io and Europa, will form those energetic neutral atoms. And they have an effect on the magnetic field of the surrounding environment. It sort of makes it very energetic. It becomes very charged. And that creates an environment that's much more powerful than what Jupiter could generate on its own. Okay, so here we can look at the magnetic fields. Ganymede, until recently, was thought to have its own intrinsic magnetic field. Io has somewhat a quasi-intrinsic magnetic field. The difference is that it's being somewhat produced as there's more. We originly thought that Io's internal heating is due to the asthenosphere. That's the sort of the outside of outside the core itself, just below the crust out here, this outer layer in the interior of Io. It's looking to be more like the internal core of Io. So we're finding that Io has somewhat of an intrinsic capability to produce its own magnetic field, but it's likely due to the influence of Jupiter in terms of tidal heating and the fact that Jupiter's magnetic field also helps. With Ganymede, you can see it's a bit more paramount because right here we can see we have the potential for those fields to sort of circle in and perhaps form its own plasma belts. If Ganymede was by itself orbiting around the sun, it would probably maintain that magnetic field, but without the influence of Jupiter, Io would probably lose that. With Europa and Callisto, you can see it's intrinsic. We got these magnetic wave fronts right here as a result of it just interacting with Jupiter's magnetic field. All right. Now, it's interesting here because it's the simple reference to a magnetosphere. The ambient field, you can see the field at the polar strength. So this is in hundreds to over 1,800 nanoteslas. So it's a weak magnetic field comparison to that of the Earth, but it's still very paramount. And one of the things is that this is the key to understanding this famous plasma torus for Io. And you can see where we have Io itself. Io's orbit is tilted with respect to the plasma torus. So a lot of times Io will oscillate almost to the top and then towards the bottom of the torus itself. So it doesn't stay in the middle of the pathway of the torus. Io's orbit is usually at an angle. It's usually tilted with respect to the plane of the torus itself. Well, the torus is more aligned with the plane of Jupiter's equator. So we have so basically the orbit of Io has an orbital tilt where the plasma belt itself has basically no orbital tilt. Its plane is lined up with the plane of Jupiter's equatorial plane, and because that matches perfectly with the dynamics of Jupiter's magnetic field. Now, what can we say about the torus itself? Well, for one thing, this is an image in infrared, 6,731 angstroms. Those are sulfur ions. So if you block out Jupiter, we can actually map the pathway of Io's torus. So we know it's actually real. This sort of arch right up here, it more matches like a boundary between the inner and the outer part of the magnetic field. So facts about the plasma torus: it's a ring-shaped cloud of ions and electrons. The electrons collide with the ions, so the ions pick up speed. Energy is absorbed and released as ultraviolet radiation. There's light emission, which is similar to that of neon and aurora lights. So there is a lot of illumination, not so much visible, but a lot in ultraviolet and infrared and microwaves and radio waves with the torus belt. The axial tilt of Jupiter in its orbit is 3.13 degrees. The orbital tilt to the ecliptic, we have the orbital tilt with respect to the sun's equator. The dipole tilt is about 10 degrees. That's the difference between the magnetic axis and the axis of rotation with Jupiter. And when we look at the tilt of the torus, it matches that with Jupiter's tilt between the magnetic axis and the axis of rotation. So sometimes the torus itself will be sort of lined up with the planet's axial rotation. I mean, perpendicular to the axis of rotation along the plane of Jupiter's equator. Other times, it will be at that 10-degree difference, depending how that magnetic axis is wobbling back and forth with Jupiter on both sides of that axis of rotation. But the field strength is 20 times the strength of the Earth's magnetic field, 20,000 times its dipole moment, which means Jupiter is a tremendously powerful magnetic field. So we see this up in detail. So we have a ring of charged particles. You're going to get more ions towards the inner part of the torus, more electrons on the outer part, and they tend to move in opposite directions from each other, but also going in sort of spiral curves. One goes counterclockwise, the other one goes clockwise. And yes, they sort of interact together. So we see the orbital inclination. It's about 0.05 degrees to Jupiter's equator and about 2.2 degrees with respect to the ecliptic. And that's the 10-degree difference. And we see that 10-degree difference. So what we have is that Io's orbit is actually spinning around, and it circles around the planet, aligned up with the axis of rotation, perpendicular to the axis of rotation. So it's almost close around Jupiter's equatorial plane, while the torus itself is more aligned with sort of like the magnetic equator of the planet itself. So we look at the tilt of Io's orbit with respect to the plane of the plasma torus. If you cut across that donut, it's a 10-degree difference. Same thing, the difference between the axis of rotation and the magnetic axis. So as Jupiter sort of wobbles about on its axis with respect to the magnetic axis, rarely you're going to get Io in the center of that plasma torus. It's still going to wobble around along the edges, where Io is at the top edge of the torus, and then it's going to be at the bottom edge of the torus. So how does Jupiter's magnetic field compare to the Earth? Well, it's very different. Why is that? Because of the nature of what we have here is the plasma material. So here we have the northern hemisphere, the southern hemisphere. We have the equatorial view. This is from the Juno spacecraft. We see the magnetic flux. We have what we call the great blue spot and the South Pole. So there's sort of, there's where we have here where the north and south magnetic poles of Jupiter are not exactly 180 degrees opposite from each other. And unlike the Earth's internal dynamo, the parts of the field do not favor either pole. So the magnetic field can flow one way, then it can flow the other way. So it's north-south, so it flips. And we get the liquid metallic hydrogen as a conductive material. So it's like a sort of a soft metal moving around the sort of the rocky core of Jupiter rather than having it be inside the core itself. Because we don't have much in the way of liquid rock to move the material about. So here, the magnetic field of the Earth is more uniform with most of the, you can see where we have, in terms of the change in the magnetic field, we see it with Jupiter is more concentrated towards the northern part of the planet, whereas with the Earth, we see it more spread out in terms of negative areas and positive areas between the North and the South Pole. So it's really interesting. The Earth core mantle boundary, well, that's at around 3,485 kilometers from the center. With Jupiter, it's at 90 at point Jupiter at 0.9 Jupiter radii, or much further from the center itself. So we get a lot more of that dynamo effect deeper between the less dense metallic hydrogen versus the more of the metallic hydrogen ice, whereas the Earth, it's more towards the equator itself, towards the core. And the Jupiter's belt versus out of the equator, we see the range of magnetic fields. Jupiter's field at the equator is very powerful, even with the Earth, which is no more than 0.85 Gauss. Now, to put that in perspective, the Earth on average is about half a Gauss for its magnetic field, which tends to be about anywhere from 100 to 1,000 times the strength of your typical refrigerator magnet. So that even then, the Jupiter's B field, even though it's much stronger than that of the Earth, it's still pretty weak compared to what human beings can do. So in terms of the atmosphere itself, I have this in different colors here, but you got the sulfur, the gaseous sulfur, that's a bluish green color, that's intermixes with sulfur dioxide. And when you go from 2 to 3 to 4 to 5 sulfur atoms bound together, it becomes crystallized and it has more of that sort of that reddish color. But the tidal forces, as Io interacts with Jupiter, it's supplying those, that sulfur material is being erupted internally, creates these huge plumes that erupt like 500 kilometers in Io's atmosphere. And that material is what builds up the torus that circles around the planet. So here, I probably should have changed the color, but the S3 and the S4 sulfur, those are 3 sulfur atoms or 4 sulfur atoms bound together. They tend to create this sort of reddish color molten fluid. Although the bulk of the magma of Io is still iron. It's mostly iron-based magma, but with a high sulfur content. And then for the S8 is where the sulfur turns into a more yellowish color. So that's where we have the more crystallized sulfur. The white areas, unlike the Callisto, Ganymede, and Europa, the only volatiles we find is frozen sulfur dioxide. Anybody know where the frozen sulfur dioxide will be on Io? We see where the white patches are. That's the frozen sulfur dioxide. That's it. No water, nothing else. So it's like a white frost on the surface. These are the auroras that you would see in ultraviolet. And those are the eruptive materials. Those are where we have intense radiation readouts from the eruptions, and they contribute to the aurora activity as that material interacts with the magnetic fields between that of Jupiter and Io. Now, here we got the warm and the cold inner torus. The inner torus is spiraling into the planet itself. It loses its rotational motion and starts to fall into the planet. Whereas the warm outer torus, it actually picks up energy and it swells outwards because then it can better escape from the planet's gravitational field. So in terms of all this, this is just be aware that it's mostly going to be sulfur compounds, sulfur dioxide, salt, sodium chloride. There is the white sulfur frost. The source of the salt itself remains a mystery because we're not sure about the origins of the chlorine, but mostly you're going to get sodium, potassium, oxygen. You'll get chlorine itself and sulfur compounds. And what we get here is that it represents the sulfur, the sulfur dioxide, the sodium, and the salts. Those are the 4 main ingredients for Io's plasma torus. Now, the field averages about 74 kilometers per second as it spins around in a period of about 41 Earth days. Io's orbital velocity is about 17 kilometers per second. So the movement of the particles versus now the flow of the energy field is moving at different speeds in the torus versus that when you compare it either from that of Jupiter or compare the orbital motion compared to Io's speed as it sort of circles around the planet itself. and it actually swells Jupiter's magnetosphere about twice the strength. Because if you cancel out Io's torus, you cancel out the effects, you find that with just Jupiter's magnetic field itself, it should be only half the strength. That's what's being measured. And then you have to remember that the field lines are what are responsible for playing a huge part in not only Io's auroras, but also Jupiter's auroras. And the material in the torus is being swept up by the Ionian atmosphere. It's being built up as it's being blown out by the Ionian atmosphere at about basically a metric ton of material per second. So there's a lot of material being exchanged around here. And this is where we have it at both at 685 angstroms and at 6731 angstroms. So you can see the intensity of the ribbons. You see the cold versus that of the warm torus. The warm torus tends to have a high concentration of light ions and electrons, and the heavier ions are going to be more towards the cold torus. I know I'm running short on time. I'll just say this here. You got the torus itself. It wobbles around the planet itself. So you see the torus as it sort of processes around the planet. In terms of the amount of energy, if we were to equate that in terms of temperature, the particles can be anywhere from 100,000 to 1,000,000 Kelvin. And it actually equals the rotational period of Jupiter's magnetic field. We know that Jupiter's magnetic field actually spins at 9 hours and 55 minutes. Io's torus is not affecting that, because Io's torus is being manipulated by the planet, whereas Enceladus's torus is actually manipulating the planet Saturn. So it tends to be the reverse. This is a nice painting I saw on the left from the Galileo spacecraft. The green area right there is going to be the ultraviolet auroras emanating from the moon itself. And there we can see the influences of Io on the aurora itself. And usually you get these hot spots. Right here, this actually comes from the ultraviolet emitting spectrometer. So you can see the presence of the particles and the types of elements in Jupiter's upper atmosphere around that aurora ring that are coming directly from those plasma belts, those belts of charged particles flowing along the magnetic field lines from Io towards Jupiter's polar regions. So you can see where we have the spots. So right over here is going to be Io spot. It's the most intense. Here is the dynamic effects as the magnetic fields of Io interacts with that of Jupiter. We got Ganymede spot and we've got Europa spot. This is from the Hubble Space Telescope. So you see the time lagging. The blue areas can also represent caldera eruptions as a possible source for Jupiter's aurora. So it's not just material being blown up by the atmosphere, but when there are huge eruptions of Io's volcanoes, well, that can cause the material to really cause these ring effects within this interesting sharp ring of the aurora activity. As you see, it's clearly defined where we have here in the inner polar regions, where you have a lot more of those hundreds of vortexes in the north polar region of Jupiter, where the dynamics of the aurora is a lot different. So we have to remember this is like a big electric circuit. Basically, it forms a 400 kilovolt battery across the planet Jupiter. The plasma belts themselves, a flux tube, which is a tube of plasma that flows along the magnetic field. That's going to be about 3,000 kiloamps. So you're dealing with 3 million amps of electrical current. And basically, it can create, within just the flux tubes, you get close to about over 1.6 trillion watts of electricity. And primarily, that's just due to the darkening of the clouds with sulfur and oxygen ions that are actually coming from Io, because you can match that with the chemistry of Io. And that darkening is the effect of the charging up of those plasma belts. Basically, if you turn all that thermal energy, it's a great source of geothermal energy, because look at the generation of those hot spots. You get about 250 trillion watts between that and the interactions of Io with the hot areas of Jupiter. Now, here is a layout of the belt itself. One of the things we have here is this, it's about 6 Io 6 times the radius of Io. And Io does have an ionosphere. There's volcanism due to gravitational interactions. Much of the material will get swept up in Jupiter's magnetic field. Eventually, it's going to circle around and escape into the environment between the planets, the interplanetary medium. The torus itself is very interesting because of the motion. Every 20 hours, the material is moving around the Io. It forms outwards into this banana-shaped cloud, which has the neutral sodium, neutral potassium, oxygen, and sulfur. And if we look here, there's what we call the co-rotational drift, because the torus itself is moving as it orbits around Jupiter. It does it faster than Io. So if we compare it with respect to Io, as Io is moving around the planet, the material, the ions and electrons are moving at 57 kilometers per second faster than the planet itself. And the material generates an electric field that moves outwards. The electrons and ions are gyrational, so they're sort of circling in different directions. I think the ions go counterclockwise and the electrons go clockwise between the inner and the outer torus. And that actually creates this interesting outflow of a magnetic field, of electrical field. It's only 150 millivolts per meter, but it's there. And here we can see the material between the cold and the hot torus. This is the NE is the number of neutrons, about 2,000 per cubic centimeter. We get the temperature of the ions at around 100 electron volts, the electrons at 5 electron volts. So the hot torus, the cold torus itself, you can see it's just 1 electron volt. So it's very, very cold temperature, but you get a lot more electrons and you get a lot more ions than electrons in the cold torus. In the warm torus, it's a lot more electrons and ions, but those ions are at much higher temperature. And you can see how this material is this is the immediate effect of the blowout from the eruptions of Io. You see how it thins out and spreads out on the opposite side of that of Jupiter. So altogether, we're looking at lots of ultraviolet radiation. The torus itself fills about 14 trillion cubic meters. Each heavy ion carries about several hundred electron volts of energy. The energy is completely thermalized. It's a very large dominating electron population. So there's a lot of electrons, which will excite any of the neutral atoms and ions in the system. So you get a lot of ultraviolet radiation from the plasma being cooled at around equivalent to about 2 billion kilowatts of power, because the only way to cool that material without the torus being dissipated is for the energy to be radiated out at immense amounts of UV radiation. So this shows the particle flow and the energy flow. Basically, it's an intermixing of ions and electrons. You've got your assortment of different oxygens and sulfurs. You've got your neutral atoms. There's the transport. There's the ions and electrons interacting together. And it shows a balance of all the energy taking place in the system based on certain amounts of sulfur to that of oxygen and sodium. The total mass of the torus is about 930,000 megatons, and it loses about 300 million teratons over a period of 4.56 billion years. So the loss is about only 1/3 of 1% of that of Io's mass. And when that total energy is excited and it accelerates from the ions, going from orbital to co-rotational, that is, it sort of moves with the moon itself versus being in its own sort of orbital rate around Jupiter. That energy is moving back and forth around 4 billion kilowatts. So there's nothing about this system that is simple. So here we got the magnetic field. We got these plasmoids because with the torus itself, the lumps of plasma will actually break off due to the spinning of the planet. So as Jupiter spins, the gravitational field will have an effect on the torus. Lumps of material get split off and it just travels outwards along this radial current that's traveling along the magnetic tail. Okay, so all this shows right here is the effects of mass being moved outwards. There is radial inward diffusion because of how we have particles around the plasma field that coming from the sun. It moves towards the planet while the torus itself is spreading its material outwards. So in terms of the radial itself, it's the material that moves outwards. There's the azimuthal because
that's dealing with motion along the orbit itself in terms of how the material is flowing about. So we have the formation of the radiation belts in the inner magnetosphere. The plasma is slowly leaking away. We have sort of this interchange between material coming in and the hotter material being moved out. And the B field itself, as it sort of circles around, the plasma drops from about 2,000 particles per cubic centimeter down to around 0.2 particles per cubic centimeter. And so the torus itself actually swells outwards to about 35 times the radius of Jupiter. So it covers a much larger volume. I mean, if Jupiter was the size of a marble, Io's torus has enough material, but if it continues to expand outwards, would basically fill this room. So the torus does pick up speed in terms of the plasma. The current itself bends back against the azimuthal part itself in order to have that enclosement within the torus to keep it stable. The co-rotational breaks down. The plasma particles around Jupiter are moving slower than the planet's rotation. That's up to 20 times Jupiter's radius. To get out to 40 Jupiter's radius, then you have the outer magnetic field, and any material that makes it out that far, if it doesn't become cold and dense, even though it's thinning out and getting hotter because the particles can then react better with more space between them, that material will just eventually will escape out in a direction away from the sun. So it's not like Jupiter holds on to all its material indefinitely. So we have the flux tubes. There's this Rayleigh-Tyler instability where you have a dense cold fluid versus that of a hotter, less dense fluid. And the cold dense fluid would be the plasma in the outer torus belt, and in the B field, Jupiter's B field would be the light fluid. And it creates these curling effects. And what's important about applying this concept between a dense cold fluid and a hot, less dense fluid? Well, it's one thing about how we form those flux tubes, because you have something called the Hall effect, where the layers of the atmosphere are charged plates. And you get charging up a positive, negative charge, you get electron transport. That's going to cause these inward flux tubes and outward flux tubes in terms of where the energy is moving between the inner part and the outer part of the torus, between the heavier, colder material, the more ions in the inner part, versus the higher energy ions, but more of the electron concentration on the outer end itself, and the less dense ions. And that actually creates flows between, it creates more of that Hall effect between the flows, because then you get something called, anybody familiar with Alfvén waves? Or Alfvén waves? Well, these Alfvén waves are what's going to be occurring with these flux tubes moving back and forth as you create that Hall effect, where they're creating like sort of two charged layers of positive and negative charges, not only around the environment, around Io's atmosphere, but how it affects the plasma belt itself. All right, so here we can see where we have the hot pickup ions, we have the cold, dense ionospheric plasma. There's the material being built up along the sides. It's trailing back from the planet. And then where we have the current sheets is where those charged particles that can flow along the magnetic field line are traveling upwards and downwards. We got current sheets coming from the planet as it reacts to material from Io being lifted up towards the polar regions of Jupiter. So this is sort of like a high voltage Hall effect, where basically you get charged plates and charged layers of positive and negative charges that are bending the fields, transporting the material, and creating this dynamic effect of Io's magnetic field. So here we see the phases of the oscillations. The Alfvén waves basically allow electrons to accelerate within the torus and create these sort of decimeter electrical waves. That's in increments of 10 centimeters each. It's very synchronizes. It causes this modulation as the torus allows this even flow, these waves of energy between the ions and the electrons between the inner and the outer torus itself. So it helps create this, and basically it helps create this intrinsic dynamo as Io passes through its own torus. That oscillation back and forth actually shifts around the charges within Io's interior and actually helps it to maintain an intrinsic magnetic field. Well, one thing they find with the ambient field, just with Io itself, they find that Io has an abnormally sized iron core in the same tradition of that of Mercury with respect to the area itself. So mostly it would be extrinsic without Jupiter being nearby, but with Jupiter's playing a part and with how it's interacting with Io's torus and how Io's torus is being affected by Io itself, it sort of reinforcing Io's intrinsic field internally. So this all deals with the nature of Alvin waves, of how radio waves are bouncing back and forth, particularly between the high density and low density plasma, between that of Jupiter's ionosphere going from the north to the south. Here's the plasma torus. So this is going up and down itself. And this will travel all the way to Jupiter's ionosphere. And that sort of stimulates the aurora activity with those Alvin waves. Very good for looking at with radio astronomy. And I think the DAM cores themselves, which actually are no more than 60 degrees of latitude in Jupiter's upper atmosphere. So you can see sort of these beacon cones of material radiating from the polar regions. And those are like big sort of DAM radio dishes, and where we get an area in which you can scan that area right there and get the pulsation effect from those radiation fields. I know I'm almost out of time, so.
I have a question over
Yeah.
here. To pull you back.
Mm-hmm.
Any of the planets. What is it inside interacting that actually creates this magnetic field?
Depends on the type of planet. Like in the case of the Earth itself, the Earth's outer core is mostly just a silicon and sulfur and a bit of iron. So if the sulfur gets charged up, it becomes negatively charged, and the silicon becomes positively charged. And so that's just the polarity of the charges. The sulfur and the silicon are more fluid than that of the iron. So those cones are going to be more of that swirling cones of sulfur and silicon, mostly silicon with a bit of sulfur, because the Earth is mostly a ball of silicon and oxygen. And that's going to be swirling around, and it's going to sort of, as they swirl around, they create these sort of hot waves around the surface of the inner core, which is mostly iron and nickel.
Now there were
With the inner core itself to create the polarity of charge.
Now one of them you showed us, it actually looks like a typical magnet. The fields around a magnet.
Yes.
How is that created?
You mean in terms of just, well, I gave you a basic example of a magnetic dipole with a magnet bar. But the thing about the Earth is that the north and south poles actually flip back and forth. It's all a matter of how the fluids are flowing inside the planet itself. That dictates the direction of the magnetic field because of how the material is being moved around by the positive versus that of the negative charges.
Okay.
There's a lot more material to cover here, but I'm sure we are short on time. So 10 more minutes? Okay. All right. So we'll go through that. Interesting is magnetohydrodynamics, because you can use a lot of fluid mechanics to see how the fact that Jupiter's Io-Taurus interaction is what we call a big Alvin wave machine. So we get these interesting radio waves that are oscillating back and forth, not only inside the torus, but how they're magnified inside the torus. They stretch out along the plasma belts from the north and the south, and they'll actually create these huge sort of radio beacon fields around the ionosphere in the polar regions of Jupiter. Okay. Right here is where we look at the different types of energies. We've got the polarized decimeter emissions. We've got the kilometer wavelength emissions. We've got the hectometer wavelength emissions. 10 hectometers equals a kilometer. This here shows the radio frequency versus that in the seconds from 0 to 20 seconds. So you can actually map out the different radio intensities at different frequencies. And here we can see that layout. There's what we call the geocoronal effect, and so we see the auroras. And so this is sort of mapping out at different planes in the torus itself, as you can see right there. And we can see how we look at the differences in the brightening of Io's plasma torus. We have the hot electrons. Those electrons are coming from the magnetotail from solar radiation that travels backwards. You usually when you get solar radiation coming from the sun, it travels around the magnetotail. The magnetotail snaps, you get a backflow effect. and that really charges up the upper atmosphere of the Earth. We get the same thing with that here of Jupiter. So we have there's a lot of precipitation of electrons. We got this sort of this brightening from the Io plasma torus, and we can see that brightening here in these radio signals right here in the short range and the high range. And you get like it's like going out in, I think this is like I did a little bit of experiment with radio waves and AM radio, where when Jupiter is at opposition and Io is passing in front of it, you get these short bursts, which is like beacons, or like beep, 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 short beeps that you can get in AM radio. And you out in the desert, we don't get many radio signals, whereas you get the long, straight chirping noises, like long bursts, and that's due to the sort of the back effect in the system, usually from those decimeter readings. Okay, so this is what I have here in the, I don't know if this will work. I mean, you can get 40 trillion watts of power in terms of the radio waves that are interacting, because this is like a beacon of energy that actually can travel all the way towards Earth itself. So these can traverse for long periods of time. Let me see if I can get that too. Oh, you know, we probably don't have any acoustics here. So, well, the S bursts will be like, and then you have the long bursts, which are like sort of chirping noises. So it's very interesting effect. So with Europa itself, one thing about Europa is that we do have oxygen snow that precipitates to the surface. We do have the possibility of eruptive plumes of ice sublimating by radiolus, in which radio waves from Jupiter's magnetic field is breaking up the hydrogen. It creates the thin oxygen, ionized oxygen torus that actually flows around Io's, that flows around the orbit of Europa as it goes around Jupiter itself. It does form these eddy currents, or are these weak electrical currents, and it somewhat bends the magnetic field around Europa, so it creates sort of this sort of weak magnetic field around it. It's not very strong, but it's mostly due to the presence of the fact that Europa's torus is mostly made of just water. I mean, you got molecular hydrogen, you got ionized oxygen, you got O2 molecules, you get heavy water, you got H3O molecules. Right here, we can see the differences in the fields when looking at Europa, both in terms of the background field at the poles or at the equator. So it's a lot weaker than that of Io, but the field itself can vary in terms of its distance. The gas content of Europa's Io torus is a neutral cloud, but it's much greater to that of Io. I mean, you've got the escape rate is around 2,000 trillion particles per second. The O2 is around 500 trillion per second. So you have this immense cloud of mostly, see, the sulfur and oxygen cloud population of Io is greater than the oxygen population from Europa. But if you think about it, you have triple the amount of hydrogen in Europa's torus compared to that of Io. And so what it is that between 7.4 to 7.8 Jupiter radii, Europa's torus literally dominates with huge amounts of water-sourced hydrogen ions coming from the breakup of water molecules. That's a good indication to show you that that Io is deficient in water. So it has a tenuous atmosphere. We got water, we got hydroxides, we have molecular oxygen. So it's a very, very thin atmosphere, but we can measure it noticeably by altitude from the planet's surface. And here we can actually look at the electron interactions. There is some dissociation. There's some exchanges of charges. There's more hydrogen and oxygen in the gas torus than the local atmosphere. So much of the atmosphere of these moons get built up in the torus. The residence times for the species, that is the time they stay in the atmosphere on Europa, is significantly different by a ratio of 2 to 1 of the molecular hydrogen to oxygen. The escape rate into the neutral cloud is 10 times greater, but we can look at how many ions are escaping into the inner and outer torus, not only in terms of the number of particles per second, but also in terms of square centimeters. So you have that outflow as a flux versus to that of time. And here we can look at the nature of comparing Io's to Europa's atmosphere. So over here is going to be Io's torus. You can see how it maximizes here at Io's orbit. Over here is Europa's orbit, and you can see that peaking of the hydrogen and oxygen. And then you have this sort of fade, this sort of ramp region where you have the overlapping, where Io's outer torus begins to decline in influence, and the inner torus of Europa really begins to build up. But look at the peak of the oxygen and the sulfur in terms of column density. You can see it's much greater with hydrogen around that of Europa at its orbit. Then we see the sulfur and the oxygen with that of Io. So Io's torus is much more spread outwards, but in terms of concentration, it's much greater at a narrow range with Europa's torus. And there's the speed of the particles and how, and again, you have the co-rotational velocity compared to Europa's orbit as it goes around the planet. But we got 20 times the reduction of molecular hydrogen compared to ionized hydrogen, and 10 times the production of ionized hydrogen near the European surface. So Europa is the greatest source of hydrogen in Jupiter's torus. So there's the gravitational sphere of influence, and that how it affects the presence of the neutral clouds around the planet itself. Okay, and then right here, we look at the effects of the oxygen itself and the influences of radiation, both from the electrons and from the oxygen at different frequencies and the different brightness in the radiation output based on the number of particles. And then right here, we can do this in a much more colorful image. So we can see the effects of Io's torus compared to Europa, the movement of material, the movement of energy, the influences from the sun. And we can see that we have sort of the intense radiation that's causing this flexing of the field with Europa. Ganymede has a mini magnetic field, mini magnetosphere. And then we have this sort of sophisticated coupling between that of Io versus that of Jupiter. Now, in terms of what we have for Ganymede versus that of Europa, there is some degree of carbonic acid, methanol, and carbon dioxide, and also ozone and hydrogen peroxide. More that's coming from Ganymede than that from Europa. But we also have some hydrogen disulfide and sulfuric acid. So we have a much more interesting array of sort of colorful particles. And we do get that alpha wave shift right here. Europa, of course, doesn't generate alpha waves with Jupiter. The inner moons, even though it has a very substantial magnetosphere because of the water particles, but they all are what happens is that Io's torus, Europa's torus, mostly serves as a primary source of hydrogen for Jupiter's magnetic field, more so than that of the sun, while all the energetic generations are going to taking place with Io's torus. But also the outer manipulation of the outer torus is also due to Ganymede's torus. And this just shows the nature of the magnetic field compared to that of Europa and Callisto. Europa's field is very minimal, while Callisto's field is much more noticeable in terms of how it influences its surrounding environment. The graphs here show the changes in the magnetic field comparing Europa to that of Ganymede. And that actually can tell us a lot about whether or not there's actually any oscillations taking place in that magnetic field because of the shifting material. Why? Due to water. And the one thing about that shifting in the graph in the upper left is that if we get the Europa Clipper with its magnetometer to see that shifting, that's going to indicate there's actually water below the ice, because that when you have water moving around, it can actually shift around the strength of the magnetic field because the moving of charged particles of salts. Because the one thing about Europa's magnetic field is the movement of water. The Rossby wavelengths as long as that of the moon, shifting around the moon itself, warming the water, charging up the particles, the salt, the charged particles within the salt, ionizing the chlorine and the sodium and the potassium and generating that electric field and inducing a weak magnetic field in the interior of Europa and emanating outwards. So,
I'll briefly go through the magnetosphere of Ganymede. It does have a conductive fluid iron sulfur core. There's the rocking of the moon, so the magnetic field sort of matches with the data as it rocks back and forth, and that indicates the presence of a huge subsurface ocean water, because if it didn't have it, the magnetic field wouldn't be rocking as much, as you would see there in the magnetic readings. I'll just quickly go through this in terms of the fact that Callisto and Ganymede do not form any ionic torus. While Europa does, magnetic field does allow it to have a nice sort of complex atmosphere. It's very tenuous, but it does contain a lot of molecular and atomic oxygen. It does have, there is a, I should probably read that more properly. There is the dissolving of ice around the icy crust to create a layer of molecular oxygen snow. We got electron dissociation. We have separation of oxygen from the hydrogen. There's possible evidence for an ionosphere, but it's probably due to the neutralization of the atmosphere of equal positive and negative charges. We have an electron density of around 4,000 to 2,500 per cubic centimeter. So the atmosphere is very charged. So it indicates a possible ionosphere. Not a lot of sodium, but there's a lot of atomic hydrogen that can extend up to 3,000 kilometers from the surface. And so that gives it a nice sort of hydrogen corona as it trails along its orbit around that of Jupiter. But it's all confined within Ganymede's magnetic field. And there's an example here of Ganymede's magnetic field itself. It has its own strength. It has the orientation. It's very well defined from Jupiter's magnetic field. It's very permanent. And it has no bow shock, but the convection is believed to be very similar to that of the Earth's interior. But it also could have a highly conductive subsurface global ocean. If it has an ocean, it's going to be more extent than that of Io's ocean. It would be hundreds of miles deep rather than being 100 kilometers deep. So, I mean, you think Europa would have very deep oceans. Oof, Ganymede would probably have even deeper oceans. But the fact that it has its own magnetic field indicates probably a very likely liquid ocean. But the ice sheet itself would be about 5 to 10 times deeper than that of Europa. So getting to it would probably be impossible. And there's where we have sort of the flow of the magnetic field on the right. On the left, the lines going up and down is going to be Jupiter's magnetic field in the background. And right there, we can see it at different angles right there. We have the rocking effect. You can see the sort of the blue lines on the planet, on the moon itself, is where we have sort of the auroras taking place. And those are going to be rocking back and forth at different angles, oscillating, indicating a planet where it's in a moon, which internally is having a lot of fluid being swished around, possibly due to the movement of some sort of fluid. And if we look at that balloon of we know it's magnetic dipole, we know its magnetic axes. Its north pole lies below that of its orbital plane. It does do some reconnections. The magnetic field travels for several radii from the planet. The magnetic field lines are enclosed at a certain range of latitudes. But north of that, the field lines are open with Jupiter's magnetic field. So you can see how a difference between that of a perturbed versus an unperturbed. The unperturbed magnetic field on the right there, and that image on the lower right, on the lower left, is more befitting of that of Ganymede. And so we get the downstream, we get the forming of a radiation belt. It has one radiation belt, mostly of ionized oxygen, and possibly it has its own sort of auroras, which we have some images of X-ray auroras. But there's a lot of sputtering of ions that are basically darkening the surface, because you have the planet lose its supply of oxygen and hydrogen, and the surface starts to darken with carbon. So we have carbon-rich darkening of material. And I'll just finish this up here. You can see where we have the auroras. I think that's going to be in the X-rays and in the ultraviolet, but those green patches show the positions of the auroras. And this is more that of a perturbed dipole on the right. When we talk about a dipole, a north pole and a south pole, and that's the result of a lot of fluid being pushed around. You don't see this with the Earth's magnetic field, because if we did this with the Earth, imagine it having oceans 1,000 miles deep in order to have this effect, which means water would have to represent a much larger portion of that of the moon itself.
So you can see the magnetic field lines, and we can simulate that to see the blowout of material from the planets in terms of the plasma belts around Ganymede itself. And it does have sort of its own bow shock. The magnetic field itself, you can see how it's very similar in properties. Well, it doesn't have a bow shock. If it did, there's sort of a question whether or not it has a bow shock, because you would need to have good sensitive magnetometers to distinguish it from Jupiter's magnetic field. But you can see how it has its own magnetic tail and a magnetosheath very similar to that of the Earth. The plasma flow on the trailing hemisphere, it's subsonic. If it was supersonic in terms of traveling at high speeds, when we sort of measure with that of sound waves, it would have a bow shock, which means with tremendous effect on the influence of the radiation of Jupiter with that of Io. And we can see here where we have sort of the influence of the dots here, where they're sort of indicative of hotspots on Jupiter, and looking at that with the auroras that we see there on Ganymede itself. So we have Alvin waves form Alvin rings. The plasma sheets create aurora spots. So we have the aurora spots. So we do see these spots of auroras on this. These images here is in Jupiter's atmosphere, and those aurora spots are marks left by auroras taking place on the surface in the environment just above that of Ganymede, which ends up being embedded in the radio waves and being transferred as sort of like an image along the plasma belts towards that of Jupiter. Let me do one more here, and you can see how we have that sort of orbital resonance, because it's 1-to-1, 2-to-1, 4-to-1, comparing Europa and Ganymede to Io, and they're all interacting together and contributing to each other's torus. And with Callisto, there's not much in the way of magnetism. It's very weak. The atmosphere is very thin. Mostly it's carbon dioxide, but there's not much of the presence of oxygen. And I would probably come back later to talk about Saturn's system. So, yeah, I know. Yeah, we'll stop right there. Any questions? Yes.
Can you say something about lethal environment that that would be in? And do we have current technology that would be providing us radiation protection against this stuff?
In terms, well, I would think a journey to Jupiter would be very dangerous. There is what they call the Outer Hopes Planetary Project. That was the HOPE project that NASA worked on, which the only feasible place to explore the Jovian system would be Callisto, because the radiation in Io, Europa, and Ganymede are at very deadly levels. And just the shielding you would need, you would have to have a very powerful magnetic field to deflect all that energy, but it would have to be very, very powerful, tens of thousands of times stronger than that of the Earth to travel in that environment. So this is from the movie Tron, End of Line. So, okay. Thanks.
Rodney, the answer to your question is no, and the amount of time is 10 minutes. A person can live in Jupiter's orbit for 10 minutes before they die from radiation poisoning.
It's like 3,600 millisieverts.
Yeah.
On Io's surface. And
yeah, lifetime of 10.
very deadly.
Right, it's lifetime of 10 minutes in Jupiter's orbit. Well, no, it's completely different though. Yeah. Okay, Rick, you got magazine just now?
That's all I got.
Very good. All right, after we get done here, we'll zip up to Mod Pizza, shoot up Middlebrook, take a left on Clear Lake City Boulevard, right in front of HEB. There's a Mod Pizza. Get together there. We will take, the pictures from our break slide are from Paul Lotz. He took these at George Observatory, a collection of pictures from Paul. We'll take a 10-minute break and get back together with the second half of our meeting.
was. Look right up. Yeah, we'll be back. Yeah, I'm sorry. No, that's what it is. Right now, I'm doing the overall mechanics, and they decided to do it. Yeah. I got the overall mechanics, I got 6 students, they're 9,000. As far as we got, the solar system process. So, right now, no, it's already started. Yeah, I'll treat you like it's okay.
Yeah, I knew I was gonna miss the first week or two. Oh, then we got all of your meeting, but that's too much. Yeah, great voice. There's something. I want great voice. Oh, no, I'm the first. Yeah, I want the whole thing. So I figured it out. I get it. I think the problem is I can't even get in the passenger for this all. They're even fidgeting. But what I can do is I can download the whole thing to my or yeah. And then I can transfer all of this to I'm driving. Even that's how I can do I bought one of the three first months. Mine was the favorite. Right. And the two. I'll find out. I made it happen. Yeah. There's a nice speed. Oh, no. They started to look at it. Yes, the history for the sky. Right. If those are you go to the I think now, so this we're going to go right and maybe and was like we're going to well, probably already the third class and say that great grab on something. Well, they how we down so you can say, not bad, we love ever so perhaps. I'm fun out something. Yeah, yeah, well, I thought, or clear, yeah, like, well, generally, you're paid, for the, you know, it's just gonna be a fun, there's a file, and they get a bit of. So it's not really. I'm just actually on like same like somebody or never count about things you got somebody either. Yeah, even I mean Yes, I was possibly rubber about it. Oh, they didn't essentially, I can't remember what they said. You had last time, so I was. I'm like, oh, it's. She had nothing else. I don't put it up. It's not like an even. It's like a- I think, no. Still not interested. The more Jamaican study. Or and. Right, well, information about what exactly about it. And I think I have people who are going to be just in time. I mean, I don't see any stuff. If you have a feeling. Raining just being umbrella. Yeah. Yeah. Over there.
Yeah, we'll start up.
But also, I don't get when that's going to happen. I found the American.
I was gonna tell you about my history versus the, yeah, or no, later.
Yeah, I'm not going in the dark. I gotta go.
No, I gotta get out and.
Out of the meeting.
We'll make sense. I'll catch you right at the end or something.
We'll get everybody coordinated here. Okay, so 10 minutes is up and we're gonna get started. We're gonna try to get started. It's always the same people. Our main speaker won't shut up. Okay, we're trying to get started here. Three times. All righty. First up here, we got Al Mowry. What's up in the sky in, oh, I'm sorry, wrong month. And recent astronomy news. Al.
I did a real short, brief one this time. Hopefully this is exciting. So I always do meteor showers. There's nothing really in June, but I thought I'd warn you about July and Aquariids. So it's not till later in the month, so we'll get another chance to talk about that in July. Very first object, binocular object. So I've been picking a bunch of globulars because they have very good brightness. Things like galaxies and nebula are hard with binoculars because of the low surface brightness. So if you've noticed, I've been picking out a bunch of globulars. And did I spell that right? Orphe? Yeah. Yeah, I think that's misspelled. I was going through the pronunciation of it. Is the hardest constellation to remember how to pronounce right. Orphe. I'm going to skip that. So M14, there's nothing really spectacular about that. M12 is a little bit larger and is very pretty as well. But normally in my talks, I've been trying to do the zodiac constellations, and this month would have been Virgo, or not Virgo, Libra, but Libra doesn't really have a lot of really good deep sky objects in it. So I sort of went with Orpheus. I tried one more time. Okay, the next good telescope object. So on the left is a zoom in of this. And it's a really neat galaxy because it has a lot more structure and it's not a perfect spiral. And the right object or image shows you kind of like what you'd normally see in a telescope. And so I think this one's really cool because it has different kind of structure to it. NGC 5605. The next thing, a friend of mine who does a lot of astronomy, he's been doing astronomy for like 30 or 40 years. I've never really spent a lot of time splitting stars, double stars. And he was telling me about the double in Lyra. So we were looking at that, and that was really cool. And it started me thinking about seeing quality. I have a very large telescope, and seeing quality is very important for it. And so I was going to start looking at double star splitting as a way to see the quality of seeing at night. And with this, we could compare his telescope, which is a bit smaller, and mine, and try to see, because his is a refractor, and refractors are sharper, not necessarily brighter, but sharper. Yeah. Refractors, you can only kind of go to a certain size. 5 or 6 inches, pretty large for a refractor. But it was really interesting to look at the different things. And then when I was studying this, I came across the Pickering scale. I never noticed this before. One of the things about doing these talks is I've done a lot of studying and investigating things I wouldn't normally do. And the Pickering scale was invented to show the seeing quality around stars that present like a sparkling kind of halo. And I couldn't figure out if they were like defocusing the star to look at the amount of twinkling, if you will. But if you look it up, there's a couple of really popular sites, and this one is one a lot of people use, and they're small little videos, and it goes a scale from 1 to 10, and you can use that as kind of a meter when you're doing visual astronomy to kind of tell the seeing quality, how much turbulence there might be. But I'm going to start studying this more and see what more I can learn about splitting stars and looking at turbulence to try to help me define the quality of the sky that night. Sometimes, like if you just come out of like your place you're staying and you are starting to observe, let's say in 10 or 15 minutes, maybe your eyes haven't adjusted quite enough. And then sometimes when you're sitting out for like a half an hour or 45 minutes, it seems like your seeing quality goes up. but are you really correlating that to the problem you have, which is not letting your eyes adjust enough? Next item is the Croc's eye. Now, between this one and the next slide, I can't remember if I had shown this one before, but once again, the left is a zoomed in picture and then the right is a little bit more typical what you'd see. And I like these types of galaxies because this is a ring galaxy, by the way. And when you look in the visually in the right picture, you can see that model nature, and that's really fun to look at visually and kind of see, instead of just the same little kind of blob or blur, and see some distinction in there by using your averted vision. So I like this type of galaxy. This is one I haven't looked at yet. I'm really surprised I haven't. It's called Fabergé, the Fabergé egg 4605. It seemed like the same number I used before. 5605. And one is this is sort of bluish, and it has this, as you look in the right image, it has this little bit of a tail. And so I think this would be really interesting to look at because it has this distinct nature. I always look, I'm not really going to do a lot of observing the next month or two, but I always try to keep track of supernovas that are going on. One is because over the last 4 or 5 years, I've been really blessed to see like 2 or 3 of them. And I thought it was really spectacular. I thought this would be something I've never would get a chance to do. And so I was like, now I'm on the track for it. And when I do these talks, I try to look up the database. There's databases online where you can see the most current supernovas. And then it's pretty easy because they give you a brightness, a magnitude, and most of them are in the 17 range, which is pretty far for most people other than cameras. But occasionally there's one in the 15s, 14-ish. And this one certainly at 15.6 is pretty challenging. Another object, a blue racquetball. This one I haven't seen either. I like planetary nebulas, and I like the odd shaped ones, and this certainly is. It also has a blue color, which is really fun. I think there's not enough color in astronomy, at least for visual guys. So pretty quickly, we're going to slide into the what's up in astronomy. There wasn't as many really interesting scientific studies this last month or so. These are some videos. There is a telescope, a 1.6 meter Goody solar telescope. It's one of the largest ones that has been created. Been around a while, but I looked this up just before the meeting. What I liked about this one shot is this thing is kind of like sitting in space, if you will, above the, I can't remember the name of the atmosphere, certainly in the corona, but you can see this other material descending, but this one blob is just kind of hanging there. So I thought that was really cool. There's another video, and this is really neat. But this adaptive optics, I looked it up. I had no idea how they were doing it. I was told that adaptive optics is they take the primary mirror and they have all these segments and they move them around really quick, many times a second, and then try to, that's not how they do it. That would seem to be really complicated, and maybe the first generation of adaptive optics they're doing that. But what they're doing now is they're beaming the telescope image instead of, let's say, directly into the imager. What they're doing is they're kind of sending it to the side, or they put the imager off to the side and they beam it against a mirror that I don't know how big it is. I don't know if it's several inches or many inches, but now they adaptively move this little mirror. So I don't know if it's a piece of plastic or some other material, and they're pushing and pulling different segments of it. I know that there's a thing called liquid lenses, and I don't know the technology. I know Edmunds Scientific makes them, and in some way they can change the focal length of a lens. They call it liquid. I think it's a gel of some sort, but so I don't know exactly how the adaptive optics work, but what they do is they shoot it against this, and then they ricochet it into a beam splitter, and that beam splitter then takes part of the image and then looks at it to decide how to adjust that secondary mirror, and then electronically changes the secondary mirror at the same time the other channel of the beam splitter goes to your imager. So what they're doing is they're peeling off, using a beam splitter, a little bit of the light to analyze it to run the adaptive part of the optics. And so I thought it was a really interesting mechanism. And there's one more here that's really cool. This is just so far out. And so what the adaptive optics have done is make a lot more clarity in the smaller portions of the, I guess, the ejecta coming off of the up in the corona. If you can go online, you can see these a little bit more vivid, and I think they have more videos as well. But these are some of the coolest ones. That's so neat. Number 2, water ice and debris disk around young nearby star. I just thought this was very interesting. You know, they just continue to just study more and more about different parts. And of course, exoplanets and young stars are the big hot topic right now. And so this is a hot star, and you can see, I probably could, you can see this ring here. And then this is part of the disk. They're looking at this ring and then this disk here as water vapor. And they've been able to look at, I think Cuniper is not spelled right either here. Is right either in the right spelling. But so they've been looking at the planetesimals and Cuniper belt objects for a while, but they didn't know that they could visualize some of the volatiles and some of the water vapor and stuff like that. So this is picture on the right is an artist's representation of what this image on the left is doing. And obviously through spectroscopy or some other method, they're able to look, the left graph shows you like further out and then closer in where the range of the moisture is, or the H2O. And of course, H2O means potentially life. So they want to look at young stars and moisture and oxygen rich planets that might be nearby. So they're trying to use other methods other than doing spectroscopy directly on, like planetesimals in order to see if there's a chance for life. So this is another method they're using to try to figure out which areas, what exoplanet based stars might have something we really want to study more. The very last one, this is the Webb telescope. I love this. So the left image is the most recent one, or the previous record holder for the oldest galaxy. And then the image on the right is the current one, which is not very pretty compared to the left one. So this Momo is the newest one, which is, confirmed to be the furthest away galaxy that we've found so far. But you know about the Webb, it's so exciting. Thank you.
Down here.
This will in fact be reasonably quick. All right, last Sunday, June 8th, we had one at the Hack Winery. I'll talk about that in a little bit. Next one up is actually another Hack Winery on August 1st. There's Okie Text, and then September 28th, we have another Hack. I've already checked these out to make sure that the moon will be in a little bit better position than it was this past Sunday. Normally, I like to hit a Friday and a Saturday, and getting people to understand how the moon works and that it changes about every 35 to 45 minutes with each night. That there'd be a big difference between the moon rising on a Friday versus a Sunday, and trying to get our common lay people to understand that sometimes can be a challenge. Don't have a lot yet on the calendar, but the libraries need to chime. We'll start chiming in soon as we start heading toward fall. And I think our Armand Bayou's out there is going to want another event. We also have Magnolia Creek coming out there. So I'm going to worry about these once we get past the hump of summer. Okay, real quick, Sunday, June 8th. Deep thanks to Reed and his friend, whose name I did not get. Mark Junko, Bob and Leslie, and Connie and myself were there. It was a light crowd because it was 35. It was again on a Sunday night. Obviously, it's a work night. Now, these events at the Hack Winery ran from 6 to 9. We had 4 scopes, 2 sea stars, and 1 set of binoculars. And we had a general crowd out here. I took a tour out into the field to find out where the moon was, hoping the moon was going to wrap its way around, because the moon was basically our primary target until other people started digging some other things up once the sun finally went down. Chris had a great view of Mars for a time being. There's Leslie with the binoculars, and there's our little favorite friend tucked out there in the sky. We had to wait until it cleared the trees. That was our problem. Even though the moon rose at 6:18, it took until about 7:30, 7:40 before we could start picking it out over the trees. Mark, and then Reed. This was Chris's solar setup. Leslie with binoculars with one of the patrons of the winery, and then 1 sea star. I think I got another one in there too. Bob and Mark chatting about something. Me and Connie just waiting for the moon to show up. Connie talked up a whole bunch of people about certain things. Anytime they started looking into the moon, she started going at. She went into school teacher mode, and that pretty much wraps it up. What nerve? He went for a walk without me. Neil Armstrong's dog, July 21st, 1969.
Has anybody seen the door prize bucket? Door prize bucket. Oh, up there.
All right, let me get door prizes here in a second. So look right here.
Door prize number. Alrighty, next month, we don't know what we're doing. We got 2 different people who have expressed an interest in being speakers. We got to sort that out. All right, door prizes. Did everybody get a door prize ticket? Everybody. All right, good enough. What? Okay. Somebody's saying something. I don't know what you're saying. Okay, 432. Last 3 numbers. 432. Andrew. Okay, Andrew, I have now here are the choices first. A map of the moon. I have a sign that says objects in a telescope are farther than they appear. I have some radio astronomy socks. You'd be the only one in your neighborhood with some of these, Andrew. I'm telling you. Radio astronomy, seriously? You want those? Hold on, one more. I have a 32 gigabyte flash drive contributed by Reed and Al, I think. None of this do anything for you?
I'll do the map.
You want the moon map?
Yeah.
Go find your way on the moon. All right, Andrew. All right. Next one. 441. You got a 441 anywhere? Yeah. All right, David, get on over here. That was the last of the moon maps, David. So that's the last of the moon maps.
Is there your names?
I might have some more. Hold on. We got a 32 gigabyte hard drive or flash drive. I have some radio astronomy stock.
No.
I have a sign that I lost. Where did the sign go? Oh, here it is. Objects in the telescope are farther than they appear. Oh, if you're an Axiom fan, I got a bunch of Axiom stuff. You know Axiom?
Yeah, sure.
Not thrilled about those guys?
Mhm.
I have a little doodad. You can put your camera on your telescope.
Mm-hmm.
I have STS 101 crew pictures.
Yeah.
Probably I got about 1,000 of those. Huh? I got a digital multimeter that worked the last time it was used.
Well, you got all kinds of.
I got an 8 gigabyte hard drive. David, what do you want, man?
I think I'll go with the sign objects.
All right. You get a envelope and you
Oh.
get a sign.
I think-
Whoa, there you go.
And you get the ticket.
All right, good enough. All right, one more. Then we're gonna skedaddle. All right, 446. 446. Anybody? Nobody. I know somebody's got this because I think everybody's still here. I can't believe it, but they're still here. Okay, 452. Oh, Stan, you got your sign, man. He won. You're off by one. You got your sign. Stan's been wanting that sign. Okay, Stan. Oh, wait a minute. I've lost it now. Oh, shoot. First off, let me give you a JSC sticker. Get a couple of these made by Mark. There you go. Look those nice. Use that anyway. I got some radio astronomy stock. I got maps of Saturn. I got maps of Jupiter. I got a meter that worked the last time it was used. STS 101 crew pictures. A little doodad where you can put a camera on your telescope.
Yeah.
Yeah, I figured. I got an 8 gigabyte flash drive. I have a 32 gigabyte VWO flash drive.
That'd be good.
All right. All right, good enough. Okay, thank you. Oh, okay.
No, I think these
So
are.
tell me about your.
So, I got the regular, the single camera working fine, but I started
Double camera. man.
the stereo camera.
Stereo camera?
Yeah.
I don't know
So
what that
had
means.
problems with